Although 5G relies on existing network infrastructure and concepts, there are several new features to 5G. Such features new radio, NR, and new core 5G-C, operation in high-spectrum bands mmWave with massive MIMO antenna system. The air interface between the G node B and user equipment, UE, has been named the new radio, NR. However, the interface between the NGE node B and UE remains the same as in LTE, Evolved Universal Terrestrial Radio Access, EUTRA. The G node BS and NGE node Bs are connected to one another via the new XN interface. The NR interface is designed to support multiple frequency ranges and bandwidths, low latency with flexible slots configuration, multi-gigabits per second data rates and increased spectral efficiency. The new Core 5G-C is a service-based architecture in which different network functions, providers, offer services to other NFs, consumers, through interfaces. The NFs can be placed at specific locations to fulfill certain latency requirements. This allows operators to deploy and adapt the network according to their needs. This network structure is a cloud-native, programmable, modular architecture designed to create multiple logical networks, or slices, running over the same physical or virtual resources. This design responds to the different network requirements of the different use cases. The technology behind this architecture is network functions virtualization and software-defined networking. A new spectrum needs to be introduced to ensure 5G meets the defined requirements. New frequencies will range from 450 MHz to approximately 50 GHz. High-frequency bands will deliver faster data rates and extended capacity, especially at mmWave bands, above 24 GHz. The Release 15 NSA specification defines the EUTRA, NR dual connectivity operation, whereby a UE is connected to one E node B acting as a master node and one NG node B acting as a secondary node. The NG node B is a node providing NR user plane connectivity to the UE and might be connected to the Evolved Packet Core, EPC, through the S1U interface. The E node B is connected to the EPC via the S1 interface and to the NG node B via the X2 interface. Network slicing. In 5G, not all traffic is equal. Mobile operators must be able to match different services with different levels of access. A concept known as network slicing. Many critical applications, such as autonomous vehicles and remote surgery, will demand prioritized 5G slices to guarantee a secured continuous service. The network will be sliced into multiple virtual networks running on a common network infrastructure, each with its own set of characteristics. A network slice is composed of a RAN and a core network with either physical or virtualized functions. Massive MIMO, multiple input multiple output aims to increase the number of transmitting and receiving antennas, TXRX, to have more signal paths and achieve gains in spectral efficiency. This would make it possible to provide higher capacity within the same spectrum. While conventional MIMO, as defined in LTE, uses few TXRX antennas, 5G goes further with massive MIMO by using dozens or even hundreds of antennas at the same time. Massive MIMO is expected to be used in the new mmWave frequencies, with rectangular antenna arrays in both the base station and the UE. MEC, Multi-Access Edge Computing. The 5G network architecture will support multi-access edge computing technology. MEC provides cloud computing capabilities running at the edge of the network, taking advantage of the low latency and high bandwidth provided by 5G. It is expected that MEC will foster the creation of innovative services and use cases such as video analytics, location services, augmented reality, data caching and optimized content distribution. The evolution from 4G to 5G in the transport network. The introduction of 5G promises to deliver new capabilities and new technologies that include the use of higher radio frequency bands to support additional bandwidth mmWave, faster and more efficient fronthaul connections, more reliable and cost-effective timing, and more granularity in the distribution of network functions. Network Functions Virtualization, NFV, refers to the replacement of network functions on dedicated appliances, such as routers, load balancers, and firewalls, with virtualized instances running as software. NFV's purpose is to transform the way networks are built and services are delivered. With NFV, any enterprise can simplify a wide array of network functions, as well as maximize efficiencies and introduce new revenue-generating services faster and easier than ever before. 5G NFV and Network Slicing. In 5G, NFV will enable network slicing, a virtual network architecture aspect that allows multiple virtual networks to be created atop a shared physical infrastructure. Virtual networks can then be customized to meet the needs of applications, services, devices, customers, or operators. In 5G, NFV will also enable the distributed cloud, helping to create flexible and programmable networks for the needs of tomorrow.